AI data center development is a really important theme right now. There's a lot of complex problems around grid planning. So we have some tables here describing our energy grid, and now we're going to use relational AI to connect to the database and build an ontology, our springboard, to solve different sorts of problems, doing graph analysis, optimization, and honing in on the best approach to plan these data center interconnections. To validate that the ontology can answer basic questions, we can see the concept relationship model of the ontology, understand how we represent the grid on the database. This is actually showing the network we're using for this example. We can see how in the real world all these connect as well, and do some basic queries on top of that. Try to understand our grid before we optimize the data center additions. What sorts of questions can we answer given the fact we're evaluating these data center interconnection results? So I'll look at the ontology and sort of ground our understanding, prioritizing data center requests to approve, given capacity constraints, scheduling problems, critical substations, grid resilience, predictions based on growth and load, enforce rules based on requests and graphs, scoring substations, and then prescriptive, which is optimizing the approval of the request subject to budget and capacity. Start by understanding our demand forecast, our predictive reasoner, using graph neural networks to run some predictions here. If we find it useful, we can incorporate it back in the ontology, save it in our data warehouse for future use. And it's also going to feed into the subsequent reasoning steps as an input. Based on our predicted data, we can see which substations are losing. There might be some pressure from increased demand in the future, where we might also prioritize upgrades. Let's look at our data center interconnection requests. Use rules-based reasoning to flag infeasible requests using this predictive data as an input. This will all combine with other analyses and roll into our optimization. We ran the rules-based reasoning analysis of the substation readiness, got some clear answers here on where we might have blockages. Now we're going to analyze the grid structure for criticality and reachability. Our graph analysis has come in. We can see the criticality of different substations on the grid, key bridge and bottleneck. Now we've got another input to layer on to the way we think about risk in the optimization problem. So finally, the moment you've been waiting for, optimize the data center approvals, given the feasible request, look at our grid resilience, budget and capacity levels, and then explore different scenarios. This allows us to iterate towards a potential solution and explore the possibilities. We've generated a new optimization problem. We've taken part of the graph models. We have the base ontology brought in here that we're building upon with our $300 million upgrade budget. We see most of the requests are approved, see which is rejected, and the impact on the substations. We solved across the 5 different scenarios, look at how our investments change and the outcomes for the upgrades and for the approvals. Given these different budget levels, we get an explanation about which approvals are unlocked at each budget level, which upgrades are funded as well, and the key trade-offs along the way. We see that $300 million is the sweet spot. So we have a report of our investment frontiers. Look at efficiencies. This is information we can work through with operators and with folks on the finance side to figure out the best path forward. But we've done this analysis going from a database to an ontology, figuring out feasibility, using rules-based reasoning, using graph reasoning to analyze critical substations and the infrastructure, optimizing based on approval and upgrades, doing a scenario analysis of different budget levels, and we can see how each feeds into the next, chaining all of these together to get a better understanding of the system, keep iterating and using AI and relational AI to better understand and improve our system.